in today's class. Right off the bat, I don't think we have met my good and important friend who probably would have helped some of you on the homework, Chemistry Cat. Did we do any Chemistry Cat examples in here? No, okay. Then let's definitely do a few. I think that'll help us out a great deal here, as well as wrapping up chapter 0 in terms of the material. All right, let's take a look at an example here. Sir Topham Hatt has to get to the other side of Sodor as quickly as possible. How many minutes will it take him to cross the island, 42.5 miles, if his train travels at a rate of 33.34 kilometers per hour? Deep breath. This seems like one of those nightmare algebra problems. Not only that, but it's got two numbers. We've never worked a problem with two numbers. What am I supposed to do with two numbers? Deep breath, because when you work a problem like these, there's one person who can help you out, one person who can come to your rescue, and that's our good friend Chemistry Cat. Chemistry Cat does what all cats do, and it goes purr, purr. It goes purr, purr, in order to identify unit conversions. So when we read this problem, we see how many minutes will it take him to cross the island, 42.5 miles, if Thomas traveled at the rate of 33.34 kilometers per hour. Hear Chemistry Cat there? Whenever you see a divided unit, or whenever you say per, what they're doing is really giving you a unit conversion, or a conversion factor. A hidden conversion factor that relates 33.34 kilometers to 1 hour. And you rarely ever want to start your homework problems with a conversion factor. So that means that the only other number in our problem, that 42.5 miles, is going to be our starting number. So that's actually what we're going to start our line with when we work our problem. So we're going to go 42.5 miles. I have miles, I don't want them. So what am I going to do? I'm going to say, hey Siri, how many miles in a kilometer?
1 kilometer is 0.62 miles.
That's not nearly good enough. There's a reason I stopped talking to you. How many miles in a kilometer?
1 kilometer is 0.621 miles.
1 kilometer is 0.621 miles. Remember, I don't expect you to memorize any English standard or any English to metric or English to SI. You can always look that up, or I'll always provide it for you on an exam. So we've looked that up. We have units of miles here. We want to place units where they cancel out, so I'm going to place miles down there. I want kilometers. 1 kilometer, 0.621 miles. So now I've crossed out kilometers, and I've gone from units of miles to units of kilometers. I don't want kilometers, so once again, whatever unit I have here is going to go down here. But now where do we go from here? Well, we want to jump into units of time. Do we see a bridge from distance to time? Yeah, that's where our good friend Chemistry Cat helped us out. They provided a bridge that told us 33.34 kilometers is equivalent to 1 hour. Once we have that in mind, working the rest of the problem falls nicely into place. Now crossed out units of kilometers. We have units of hours. We're not being asked about hours, we're being asked about minutes. And we know that 1 hour is 60 minutes. Once again, placing units where they cancel out. And we would just multiply by everything on top, divide through by everything on the bottom. And that would give us 123.163773. That's our calculator lie. So we need to come back and we need to apply sig figs. We've got 3 sig figs there, 3 sig figs there, 4 significant figures here. This is a relationship that's by definition, so it's exact. So our least number of sig figs is 3, so our answer should have 3. And we can see that when we use unit conversions, problems can be as easy as 1, 2, 3. But you kind of thought any question involving Thomas the Train would be as easy as 1, 2, 3. And yes, I spent way too much time thinking about that problem. Let's take a look at another quick example where we would use chemistry cat. A 0.200 kilogram piece of iron has a heat capacity of 888 joules per degree Celsius. Here, chemistry cat there, per degree Celsius. So we have a unit conversion over here that is telling us that 888 joules is equal to 1 degree of Celsius change. How many kilojoules of energy would be required to raise the temperature of iron by 53.2 degrees Celsius? Well, I still have 2 numbers, but I see one of them's temperature and I know where to go with temperature. So I'm going to start here. I have 53.2 Celsius and I am getting, just a second here. Let me see. Okay. We've got 53.2 degrees Celsius. I don't want degrees Celsius. So I'm going to place my degrees of Celsius where they cancel out. I know the relationship between degrees of Celsius and energy. So now I've gotten rid of degrees Celsius. I have units of joules. I don't want joules. I want kilojoules. I know that a kilojoule is 1,000 joules, right? The K is replaced by 10 to the third. So now I've gotten rid of joules, and I just multiply everything on top, divide through by everything on the bottom, and that gives me 47.2416. Sig fig check. 3 sig figs here. 3 sig figs here. That's exact. So my least number of sig figs is 3. 1, 2, 3. And we wind up with 47.2 kilojoules. Now I'm going to let you try this last one real quickly before I steal all your fun. Given that 4.184 joules equals 1 calorie, lowercase, and that there are 1,000 lowercase calories in 1 capital C calorie, if 398.2 capital C calories of heat were applied to a piece of iron, what would the change in the iron's temperature be? And I will try to be quiet for 1 minute while you guys take a stab at that one real quickly. It will take a lot of self-control for me today because football starts tomorrow and yesterday was Star Trek Day, so life is good.
I can't hear you, Doug.
Thank you. I forgot to turn on my microphone. I'm glad somebody spoke up. Otherwise, I would have gone on talking quietly to myself for quite some time. Not that that's any different from a normal day for me, but let's see. Those two, the numbers that I highlighted, they're obviously unit conversions. So that leaves us one number to focus on to start our problem with. So we're going to start our problem with 398.2 capital C calories. We don't want capital C calories, so we're going to have to place them where they cancel out. 1 capital C calorie is equivalent to 1,000 lowercase calories. So we've crossed out of our calories. We don't want lowercase c calories, so we're going to have to cancel them out. We want to know temperature change. Well, I see a unit conversion between lowercase c calories and joules, and I know the relationship between joules and degrees Celsius. So let's go there. 1 calorie is 4.184 joules. So I've gone C to lowercase c joules. I don't want joules, so I'm going to place joules where they cancel out. I know according to my unit conversion up here at the top of the problem that 888 joules are equivalent to 1 degree Celsius. So I'm going to multiply everything on the top, divide through by everything on the bottom, and that is going to give me and I get 1,876.2036. Let me punch that in again just to make sure. 398.2, although that does seem right. 123 times 4.184 divided by 888. All right, same number again. So now we have to do our sig figs. We've got 4 significant figures there. That's exact. That's 4 significant figures. That, however, is 3 significant figures. 1, 2, 3. Round on the basis of that 6. So we could say that we have 1,870 is our change in temperature, or 1.8 times 10 to the third degrees Celsius. You say potato, I say potato. And that's really what Chemistry Cat lets you do, is it lets you take those divided units and use them as a conversion factor. We have done density, right? Did I skip ahead to the density, or did we not get to do density last time?
I don't think we did density.
Okay. All right. Then let's take care of density right off the bat and get that out of the way as well. Density is just an example of one of those divided units that's useful to use as a conversion factor. It's also a classic example of a physical property of a substance and can be used in identification. And before the end of the semester, in 175 lab, you actually use density to identify an unknown. Density is the ratio of a substance's mass to its volume. Mathematically, density is mass divided by volume, and you can always remember it because the world's densest people work at the DMV. I said that one time, and a student responded, "Gee, I'll really enjoy sharing this one at my lunch break at the Jefferson County's clerk's office, also known as the DMV." But yet I told the joke again anyway. Oh well. Again, what does that say about me? I digress. So density is mass divided by volume, or DMV is the mnemonic device. Density has standard units, or units for which it's usually reported in. For liquids, it's generally reported in units of grams per milliliter. For solids, it's generally reported in grams per cubic centimeter. Remember, this is one of the things, according to when I went back and did the video review, as we were dashing out the door last time, I told you to remember that 1 milliliter is the same thing in terms of the amount of volume as 1 cubic centimeter. So the mass, so the density of a liquid is directly comparable to the density of a solid. Gases, however, we like to obscure things because the density of a gas is so low compared to the density of a liquid or a solid. We actually report its density usually in terms of grams per liter. A term that's not that important for people in this course is much more used a lot in the medical profession and specific professions. Well, I guess a lot of you are going to the medical profession, is specific gravity. And specific gravity frees the concept of density from temperature and pressure considerations by taking the ratio of a substance's density to the density of water at the same temperature. Specific gravity has no units. Why does it have no units? Because you're dividing a density of a substance X divided by the density of water. Well, grams per milliliter divided by grams per milliliter. Anything divided by itself is 1, right? So specific gravity has no units. Not only that, but here is something that you'll have to remember for 180. It'll make you a blast to talk about it at parties, and will save you a little bit of time on homework, and you'll probably become familiar with it depending on how Mr. Winchester is doing the lab before the end of the semester anyway. So at 4 degrees Celsius, the density of water is 1 gram per milliliter at atmospheric pressure. At 4 degrees Celsius, the density of water is 1 gram per milliliter. The density of water is only going to change a little bit depending upon the pressure and the temperature, assuming normal conditions, right? If you're going into the heart of a sun or in the vacuum of space, yeah, that's going to affect things a lot more. But on Earth, the variation of water away from that is really going to be, in terms of its density, is going to be in the thousandths place in terms of the decimal. And you'll get a chance to see that in lab. So what I'm saying is that whenever you're needing to do an estimation or a quick and dirty calculation, knowing that the density of water is 1 gram per milliliter is often assumed and is often crucial for you doing those calculations. In terms of specific gravity, it produces a rather ridiculous effect. For example, the density of iron is 7.874 grams per cubic centimeter. So the specific gravity of iron would be 7.874 grams per cubic centimeter divided by 1 gram per cubic milliliter, which are the exact same units, and any number divided by 1 is the number again. So the specific gravity of iron would be 7.874. That would be the specific gravity of iron. The density of iron, 7.874 grams per cubic centimeter. So whenever you see specific gravity, don't panic. For your calculation purposes, drop in units of grams per milliliter or grams per cubic centimeter, whichever one floats your boat. But you report specific gravity with no units. So you'll be reading a homework problem, you'll come along and they'll give you one, and it won't have that there for you. It won't have that gravity there for you. Let's see. One other thing about density is less dense floats on more dense. And I could have sworn I had an example problem here real quickly. If the density of ethanol is 0.85 grams per milliliter, what would the volume of 12.4 kilograms of ethanol be? 12.4 kilograms. We don't want kilograms. We place kilograms where they cancel out. 1,000 grams per kilogram. I have grams. I don't want them. Chemistry cat is one of our friends that constantly occurs whenever we're looking at density. That's telling us that 0.85 grams equals 1 milliliter. So I can place grams where they cancel out. Now I have a unit of volume, so I can multiply everything on top, divide through by everything on the bottom, and that gives me. Helps if I turn the calculator on. That is a good first step. I have discovered that. Calculators work better when they are on. That's the big takeaway from today's lecture. 1.4 0.59 times 10 to the fourth milliliters. Sig figs, we've got 3, we've got 2, so we should have 2 for answers. 5 is what you round upon, so 1.5 times 10 to the 4 milliliters. Chemistry's easy, life is hard. And hopefully those helped out with the last homework problems that were lingering. Yes, so density is another. There is a technical difference. I'm answering a question here in the chat. There is a small technical difference between density and specific gravity. Technically, specific gravity is the ratio of the substance's density to the density of water. That has the effect, practically, under normal conditions, of just stripping the density of his units. The boiling point of water, we'll actually save that for 180, and we'll go over the math and theory on that one, but I don't want to go too far into that right now. Let's take a look at the next chapter. We are actually finished with that chapter, so we get to go on to the next one. And you all have started this one in the pre-recorded lecture, but what I'm wanting to do is I'm wanting to go over a couple parts of it with you in person, starting with the introduction of the subatomic particles. Now, you have not listened to this in pre-recorded lecture, correct? This has not been assigned. I went over the announcements. I did not see it assigned. Good deal. All right, then let's whiz through these here. There are 3 subatomic particles that you're going to learn about right now. We'll actually learn about a 4th subatomic particle before the end of the chapter. But the 3 subatomic particles that are going to be important to us right now, and we're going to view as making up the atom, are going to be electrons, protons, and neutrons. And we're going to differentiate these 3 subatomic particles on the differences between their mass and their charge. So I'm going to draw a little chart here. And I have electrons. I have protons. Ooh, everybody write down Captain Proton. Everybody write down Captain Proton. All right. Let's take a look here. Let's start off with talking about the proton. The proton has a relative charge of +1. We say it has a relative charge of +1 because we wanted to make it easy to talk about. In reality, it has a charge along the order of 10 to the -19 coulombs, but that makes for a real mouthful to talk about if we want to talk about a difficult, long number every time we were going to mention protons. So we refer to protons as having a relative charge of +1. We also played fast and loose when it comes to mass for protons. We created a unit known as the atomic mass unit. And I'll switch back to the other slide here. We created a unit, the atomic mass unit, to allow the proton to have a mass of 1. Technically, the atomic mass unit is a unit of measure in chemistry that expresses the mass as a ratio of 1/12 the mass of the carbon-12 atom. The carbon-12 atom, as we'll talk about here before the end of the day, has 6 protons and 6 neutrons. So what dividing the carbon-12 atom by 12 does is it averages the mass of a proton and a neutron and creates a unit that effectively lets us declare the proton as having a mass of 1. In reality, it has a mass in kilograms that we won't really deal with in this class. We'll deal with the mass of an electron in this class, but not really the mass of a proton. But we will say that the mass of a proton is approximately 1 AMU. Now, protons are countered by their evil opposite, the electron. The electron has almost the opposite properties of the proton. First, it has a charge that is equal in magnitude, but opposite in sign to that of a proton. We will refer to it as having a charge of -1. Again, it's going to have a charge along the order of 10 to the -19 coulombs, but that's difficult to talk about, so we refer to it as having a relative charge of -1. Mass. Here's where I want to make sure that you understand the difference between what I'm telling you and what you may have had in a previous science course. We say that the mass of an electron is 2,000 times smaller than a proton's. Electron's mass is 2,000 times smaller than that of a proton. What that means is we refer to the mass of an electron as negligible in the context of the atom. The mass of an electron is so much smaller, 2,000 times smaller, than the mass of a proton. So when we're calculating the mass of an atom, calculating the mass of an electron is part of that consideration. We're going to see some examples before the end of chapter 2 where we're definitely talking about the mass of an electron. We're doing things with the mass of an electron, and we're really having some fun with the mass of an electron. However, when it comes to determining the overall mass of an atom, the mass of the electron is so much smaller that we don't take it into consideration. It's kind of like asking Bill Gates what his net worth is. When Bill Gates tells you his net worth, does he bother to go through his couch cushions and look for coins? No, right? Whatever coinage is in his couch is negligible compared to his entire net worth. So far, so good? The final entry in our triumvirate is the neutron. The neutron is the political moderate of the subatomic world. It doesn't want to take a stand on any issues. However, it wants to be given all the weight of someone who does. Therefore, we refer to a neutron as having no charge, and a neutron has a mass approximately equal to that of a proton. They're not equal in reality. There's a minor difference, but they're close enough that for our conversation purposes, and unless we go way down into the depths of particle physics, or unless we're looking at a career in nuclear chemistry, that difference in mass isn't really going to play a role in terms of what we're looking at. So we refer to it as having a mass of 1 AMU as well. Again, the AMU unit was basically created so that we could do this conversational ploy. And this was given to you verbatim in the handout there at the top of chapter 1, which I'm assuming a lot of you have already pulled up on your computer or have printed out or have access to in some way. Let's take some time looking at electrons and looking at the history of the electron. the electron was discovered by a man named J.J. Thomson, and he did so by playing with cathode ray tubes. Now, cathode ray tubes are really fun. Matter of fact, we had one that I was able to play with. And I had it in my hands when I was talking about the Titans, and they were on their 13-3 season. And it kind of flew out of my hand when I gesticulated, and well, they're $2,000 to replace. So, okay. Let's take a look here. Our cathode ray tube is a special type of tube. It's a glass tube that's been evacuated, meaning all the air has been removed from it. And in each end of the tube, you have two electrodes. One of these electrodes is referred to as the cathode, and it has a negative charge. The other is the anode, and it has a positive charge. What Thomson did was he applied an electrical current across this cathode ray in such a fashion that whenever he applied it, no matter what he did, the ray that was produced, when he applied an electrical current, he saw a ray produced. And this ray always went from the negative cathode towards the positive anode. So it always flowed from cathode to anode. All right, well, if the cathode is negative and the anode is positive, and opposites attract in chemistry just like they do in dating, what can we conclude about the charge on these little particles that must be making up this ray? We can conclude that they have a negative charge. Why? Because they're fleeing from the negative and they're moving towards the positive. They're attracted towards that positive. So that's one piece of evidence that these particles had a negative charge. He also applied a magnetic field to these rays and discovered that these rays respond to the presence of the magnetic field, always bending towards the negative end of a magnetic field, always being repulsed by the positive end of a magnetic field. So he had two pieces of evidence that these little particles that he was observing had negative charges. The other thing that he did that made him truly brilliant in conducting these experiments was he said, okay, I'm having lots of fun with copper here, but what if I make my electrodes out of iron or zinc or gold or tin or carbon? What if I keep changing out this electrode material? Does it affect the behavior of these cathode rays? And what it turned out is that no matter what material he made these electrodes of, the rays always behaved the same. They always went from negative to positive, and they were always present. So he concluded that all substances must contain these tiny particles that make up cathode rays, which he named electrons. He was even able to calculate the mass to charge ratio of these electrons. This is a really cool, what I think is a really cool video here. It reminds me of back when I was in high school, we had to watch these really old ancient VHSs. And somebody was nice enough to, well, what did I just do? To post one of these things on YouTube, and I absolutely get a nostalgic kick out of it. So let's watch it real quickly so we can see a cathode ray in action. And before it goes too far, let me see here if I've got my, oh good, you're still with me. All right, so sharing that. Let's real quickly share. And know it's not my computer that makes it look grainy. This is just, I'm telling you, this video has to be 1980s something.
To demonstrate a Crookes tube, a cathode ray tube.
Let me see if I can increase the audio volume here for you. Oh, come on. Not even funny.
We need a high voltage power source, such as this one. We need the Crookes tube that has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
All right, thank you for indulging my nostalgia there. All right, so Thompson got us the fact that we
How do you
have.
picture an atom in your mind?
What
Like
did I just
this,
do?
or like this, or maybe one of these? If you understand.
My turn to talk now, not yours. All right, there we go. So we have these cathode rays, and these cathode rays have allowed to the discovery of the electron, the fact that they are present in all substances, and that they have a negatively charged. We also know the mass to charge ratio. The problem is, how do we unscramble that mass to charge ratio? The solution was really, really elegant. The solution to unscrambling that mass to charge ratio is one you can actually have fun with at home. Now, I don't know how many of you have a hairdryer. I haven't needed one in a couple decades, unfortunately, but I like to play around with my wife's hairdryer there. And balloons. And here's the reason why. If I have a balloon and I drop my balloon, what's pulling my balloon down to the earth? That's not a trick question.
Would it have to be gravity?
Yeah, absolutely. Gravity, absolutely. Gravity's dragging it down there. And the speed at which gravity accelerates something has been known for a long time.
9.8 meters per second squared.
You got it. So we know our acceleration due to gravity, and force, the force with which that balloon is falling, is equal to the mass of the balloon times the acceleration due to gravity. So by just placing that balloon on a scale, I can figure out the exact force with which my balloon's falling. Well, if I want to stop my balloons falling, I can use my wife's hairdryer. Turn on my hairdryer, and my hairdryer creates a breeze back against that balloon, and with a little bit of practice I can get that balloon hovering right on top of there, right? Just like it's an air hockey puck. Yes, it's hovering right there. Well, in order to get that balloon to hover, what force must my hairdryer be exerting?
Has to counterbalance the force of gravity, right?
Yeah, absolutely. It has to be equal to the force of the falling balloon. The force of my hair dryer has to be equal to the force of my balloon. Well, Milken was a chemist, and like all good chemists, he liked playing with balloons in his wife's hair dryer as well. But it gave him an idea. And his idea was pretty simple. He said, I'm going to create a bunch of oil drops. Because I created these oil drops, I know their mass. I'm going to let these oil drops fall to the earth. If I know that these oil drops are falling to the earth, I know their mass, and I know their acceleration due to gravity. Not only that, but to make sure that this experiment is extra super awesome, I'm going to perform it in a vacuum so that there's no air friction to think about. So I've got a bunch of oil drops, and I'm going to let them fall to the earth. And as they fall to the earth, I'm going to play pool with them. I'm going to shoot X-rays at them. And these X-rays are going to function like the cue ball in Q in pool, and it's going to knock off some electrons. It's going to knock some electrons off my oil drop, and it's going to knock some other electrons onto other oil drops. So I've got this situation where I've got oil drops falling, and I've knocked electrons off of some and onto others. So I've got a situation where I now have oil drops, and some of these oil drops have a negative charge. But I still know the force with which they're falling, even though I've knocked around their electrons. Well, I'm going to stop the electrons from falling. I'm now going to turn on my hair dryer. The hair dryer that he chose to use was 2 electric plates. He took 2 plates that functioned as electrodes and ran a voltage across them. Turns out that electrical force is equal to voltage times charge. So by turning on this voltage, which he controlled, he knew the voltage, he knew the force with which it would take to get the oil drop to stop falling, because he knew the oil drop's mass and the acceleration due to gravity. That allowed him to calculate the charge, and thus he was able to calculate the charge on each and every oil drop that was falling, which made it really cool because he was able to calculate charge basically using a balloon and a hair dryer. Also, which is super cool here, he did this all in the late 1800s. So he was actually sitting there with his eye, watching those oil drops, getting them to hover, manipulating the resistance between those plates, which I think is just really cool. Now, in all honesty, I think I could have designed that experiment if somebody gave me a little bit of time to think about it. What I think makes him truly brilliant, however, is what he did with the data he got out. And this is where I have to tip my hat to him. He got a data set that looked a lot like this. He got a data set that looked a lot like that. If I had a data set like that, I would have put my head down on the desk, had myself a good cry, and began looking for a career in something easier like biology. Sorry, both my little brothers are biology majors, so throwing some shade. But if I had data like that, I would have panicked. I would have thought, I'm a failure. I'm looking at all these measurements. I've done to the best of my ability, but I don't see any numbers that are the same. So how can I get anything useful out of this? Then Milken thought, it has to do with the fact I'm a lousy pool player. Remember our oil drops. He was taking X-rays and was slamming them into those oil drops. This was really the part of the experiment that he didn't have a lot of control over. How many electrons were being moved around? And he said, okay, these different charges aren't the result of bad measurement. These different charges are the results of different numbers of electrons being moved around. In other words, I've knocked a different number of oil drops onto each of my oil. I've knocked a different number of electrons onto each of my oil drops. Okay, great. So I spent a lot of time measuring a bunch of different electrons, but I don't know how many electrons. So I'm still not going anywhere. But here's where Milken came to a great conclusion, or a great logical leap. He said whatever the smallest difference in charge is between drops must be the charge of an electron. Why? Because the only particle he assumed that he was going to be able to move between these oil drops was an electron. So he said, okay, all these numbers I'm looking at have to be whole number multiples of this smallest difference as well, if I'm only able to move around whole electrons. So he went through this data set and he said, okay, let's see, 10 minus 8 is 2, so I've got 2 times 10 to the negative 19th there. Ooh, there's another 2 times 10 to the negative 19th. There's a 4 difference, but hey, guess what? 4 is divided by 2 to tell me that I must have had a 2 electron difference between these, right? So the smallest difference he found was that, and he said, okay, now I can check my data. Are all my other measurements whole number multiples of that? So he went through and divided all his drops and found, okay, here I moved 3 electrons, here I moved 6 electrons, here 5, here 4, here 2. And that's where he really, whoa, talk about good logic, talk about good data analysis. He really rocked that one. And that's how he came up with his charge of the oil drop. And it's just really super amazing here. I mean, look at this. This guy was working in the 1800s by eye, okay? Doing that, he calculated the charge on an electron as 1.59 times 10 to the negative 19th Coulomb. The accepted value today is 1.602 times 10 to the negative 19th. In other words, with all our supercomputers, all our electronic devices, all our unlimited graduate students to throw out the problem, what do we have? We've got about a 2% difference compared to what he did with his eyes. Unbelievable workmanship, not to mention thinking. All right, so that's our electron. Oh, and once he had the charge of an electron, he could use that charge mass ratio to unscramble the mass and get the mass of the electron as well. Next, we want to talk about another famous experiment. One, if you've had chemistry before, you have probably heard of. Maybe even if you've had physics or physical science. And this is the gold foil experiment. The gold foil experiment started out as an attempt to prove what's known as the plum pudding model. The plum pudding model of the atom viewed the atom as if the atom was plum pudding. You had this nice positively charged pudding. And inside this positively charged pudding, scattered like plums, were electrons. Now, nobody in North America eats plum pudding these days, so the analogy has kind of gone bad on us. But we've all had the bad experience at the grocery store of being in a hurry, grabbing those pudding cups without thinking, without really paying attention, getting home, ripping open our vanilla pudding, and finding these slimy things in it, right? We've all had that tapioca pudding by accident, where it's like somebody put like wet gummy bears or something in our pudding. It's like tapioca pudding, where you've got a positively charged pudding with those electron tapioca scattered in it. The point is, according to the plum pudding model of the atom is nearly entirely matter. Rutherford had a graduate student who was driving him bonkers and he just really wanted to get rid of. So he said, okay, I'll give this graduate student this really easy experiment to prove the gold foil model of the atom to prove the plum pudding model of the atom so that I can be done with them. So what the graduate student did was he went to the basement of the science building and he took a thin sheet of gold, very, very thin. The reason they used gold wasn't because they had an unlimited research budget. It was because pure gold is extremely malleable and extremely ductile. You can manipulate it with your fingers very easily. Gold is so malleable in its pure form. So he took gold so that he could get a really, really thin piece of foil. Then he took, and this is something important that we need to know the nature of, he took an alpha particle source. Alpha particles, also represented by the symbol alpha, are particles that are made from 2 protons and 2 neutrons. Therefore, these alpha particles have mass and have a positive charge. The graduate student was going to then take these alpha particles and throw them at the gold foil. In order to see what happened to the said alpha particles, they took the gold foil and put it in an arena of active material, zinc sulfide, so that they could see a little green flash visually whenever an alpha particle hit the screen. Well, this plum pudding model was known to be correct by everybody. Well, you've got a particle that's mass. You've got plum pudding, which is model of the atom, which has also said that the atom's 100% mass. We've all thrown a tennis ball at the wall. What happens? Does that tennis ball go through the wall? No, not even if the Hulk throws it, right? It just bounces back, yes? All right, so expecting to play tennis with alpha particles and gold foil, the graduate student goes to the basement and conducts this experiment. And what the graduate student finds is that instead of all these particles just deflecting off that gold foil, the majority go straight through. Just like the gold foil wasn't even there. Then you had a group of particles that went through the gold foil, but for whatever reason, instead of going straight through, they were deflected. Came through at angles. Then he had a small minority that was actually doing what they were supposed to. And bouncing back at that source. So the graduate student goes and tells Dr. Rutherford, Dr. Rutherford, these are my results. Dr. Rutherford buries his head in his hand and says, get out of my sight! Clean out your desk and do something else with your life, you incompetent baboon! I can't believe I wasted my time with you. Then Dr. Rutherford sends another graduate student to the basement to do the experiment again. Other graduate student does the experiment, and guess what? Same results! So the other graduate student goes and tells Dr. Rutherford. Dr. Rutherford goes, I can't believe it! I am surrounded by incompetent morons! Seriously! I give you a simple experiment to prove something that's already known, and you can't even execute it right. If you want something done right, you gotta do it yourself. Not too good and too much valuable to do to waste my time with such an elementary experiment. But Rutherford goes into the basement of the science building and does the experiment himself anyway. And guess what? Same results as the grad students. So what does Rutherford say? I'm brilliant! And he reaches three conclusions. He says, okay, I have a majority of my electrons passing straight through my gold foil. So what can I conclude? That there's nothing there. Atoms must be mostly empty space. So since the majority of the alpha particles were going straight through, matter can't be in two places at once, so there's nothing there for them to hit, so atoms must be mostly empty space. So the alpha particles that go straight through say atoms are mostly empty space. Then he looked at the ones that bounced back. They're actually the ones the easiest to explain next. He went to the ones that are bounced back, and he said, well, some are bouncing back, so they must be hitting something. So atoms must have a small, dense center of mass. Atoms must have a small, dense center of mass. In other words, there has to be something in there for them to hit. However, since only a small minority of my particles are getting bounced back at me, that means that center of mass has to be really small. So my atoms must have a small, dense center of mass. And then here's where I think he actually was showing a great deal of thought. I could have got 1 and 3 there, no problem. You know, I could have reeled those off without any trouble at all in my days as a grad student. Where I think he showed brilliance here was with number 2, explaining those that were deflected. In order to understand what happened with the deflected particles, you have to remember these alpha particles had a positive charge. If you've ever played with a magnet, you know that if you bring 2 north ends of a magnet together, they push each other away. There's a resistance. So what Rutherford concluded was that if I'm seeing some things deflected, positively charged alpha particles must be being pushed away by something else with a positive charge. Therefore, he said, that the small dense center of matter must have a positive charge. And if the nucleus had a positive charge, what couldn't be in the nucleus? Electrons, right? If electrons were in the nucleus, then we wouldn't see a deflection of our alpha particles. So from this, Rutherford was able to put together a completely new model of the atom. And because he is such a nice guy, he went ahead and threw on the graduate students as seventh or sixth dairy authors, you know, just to prove that he was a nice guy, even though they were incompetent and couldn't do the wonderful things that he had just done. So Rutherford's model of the atom said the atom was mostly empty space, and in this empty space, the electron cloud, the electrons were located. Then, inside you had a small dense center of matter. Where the matter of the atom is located, meaning where the protons and neutrons are located. He referred to this small dense center of mass as the nucleus. And I'm sorry, this is a hard moment for me. It's something that all chemists are still trying to come to terms with today. Rutherford took the name nucleus from Hooke. That's right. That's right. Rutherford borrowed something from the biologist. I don't know why he did it. Chemists these days are still trying to live that one down, but Hooke used the term nucleus for a cell a good 200 years before Rutherford used it for the nucleus. So we're still trying to live that one down at cocktail parties. Just a second, I was on a roll there and I heard a question. Let me go back to see what the question is. All right, let's take a look here. We've got quick analogy here. When we talk about the nucleus being small compared to the empty space, your book likes to use the analogy of a baseball field, saying that if a P is the nucleus, then the atom would be the size of a baseball field. So we're talking a whole lot of empty space for an itty bitty nucleus, just like the genie, right? Ooh, write down genie. Everybody write down genie. All right, everybody write down genie. All right. Here. The rest of this chapter is devoted to a discussion of the nucleus. We are going to take a brief foray into actual nuclear chemistry. However, before we can do that, we have to define some terms. First, the nucleus is that small, dense area of an atom where the protons and neutrons are located. To describe the nucleus of a particular nucleotide or a particular atom, we use two numbers. We use the atomic number and mass number. The atomic number is the number of protons in an atom's nucleus. The atomic number and the atomic number alone defines the identity of an atom. The number of neutrons are irrelevant. The number of electrons are irrelevant. The only thing that matters to the identity of an element is the number of protons. You can find the atomic number at the top of most periodic table blocks. Why? Because it's synonymous with the name of an element in terms of the identity of the element. For example, if you look up carbon on a periodic table, you'll see that there's a big 6 above the C, or sometimes you'll see the 6 located up there. But you'll see a big 6 prominently at the top of the block. That is the number of protons in every single atom of carbon. Every single atom of carbon on the entire planet has 6 protons. What happens if it has 7 protons? Then it's not carbon. Then it's nitrogen, right? The number of protons defines the identity of the element. If you change the number of protons, then you have changed elements. That is what we define elements by, their number of protons. So it's an extremely important number. Not only does it tell us about the number of protons, but for neutral atoms, the number of protons equals the number of electrons. So our carbon atom up here would have not only 6 protons, but if it's in the neutral state, it would also have 6 electrons. The other number that we use to describe the nucleus of a particular nucleotide is mass number. Mass number does not appear on the periodic table. Mass number is the sum of the number of protons and the number of neutrons in a particular atom's nucleus. Atoms of the same element can have different mass numbers. When atoms of the same element have different mass numbers, they're referred to as isotopes. So isotopes would have the same number of protons, but different number of neutrons. Carbon is famous for its isotopes. There's carbon-12, which is the most popular. There's carbon-13, which everyone likes to forget about. And then there's carbon-14, which even though it's the smallest in abundance, is the one that gets all the dates. Ba-dum-bum! Gets all the dates. Carbon-14. Make sure you try the salad bar. I'll be here all week. All right. One way we can talk about isotopes is by writing the name of the element and then writing their mass number. So when you see a name of an element, hyphen, and a number, that's the mass number that they're writing there. The other way we can talk about isotopes of a different element is to write the elemental symbol, the mass number as a superscript on the left-hand side, and the atomic number as a subscript on the left-hand side. Left-hand side tells you information about the nucleus. One thing you have to remember is the mass number always tells you the number of protons plus the number of neutrons. Doesn't tell you the number of neutrons, it tells you protons plus neutrons. So if you want to get the number of neutrons, you have to do some subtraction. Fortunately, the way we have the symbology set up we've got that subtraction all set up for you. For example, nitrogen 14 has a mass number of 14 and an atomic number of 7. So I've got my protons plus neutrons up at the top, my protons down at the bottom here. So to get my number of neutrons, I subtract. Nitrogen 15, protons plus neutrons up top, protons down at the bottom. 15 minus 7 is 8. So now I have my number of neutrons. Chemistry is easy. Life is hard. Yes? Gosh darn it. We are out of time. That's okay. I progressed us pretty far here. And pretty much to where I want us to go. So we will pick up, so I'll be able to give you some homework to while away the long hours until Monday when we meet again. And that's it for today.
Dr. Kelly.
Have a good one.
Dr. Kelly.
Yeah.
I have a quick question. I don't know if you saw it. I tried emailing you, but on the homework that was due, I believe it was the 7th, there were some answers on there the computer was giving me that I was really unsure about. One of them being 3,000 nanometers, I believe it was the unit, and it asked how many sig figs there were, and I put 1 sig fig, and it said that there were like 5 sig figs. It said 1, 2, 3, 4, 5 were all answers.
This is the one I tried to. That's the one I tried to warn you guys about in class.
Yeah.
Remember, just a second here. Let me go where I can get some scratch paper here, and this works. Come on. This is the type I was trying to warn you about in lecture when we were going over those ambiguous zeros. And this is one of the reasons this is one of those things I dislike about your book. Our other textbooks handle these zeros a little bit differently, although this is not unconventional thinking. I just object to it. You look at that measurement, right? You know for a fact that 3 is significant. So you know for a fact that has at least 1 sig fig. At least 1 sig fig. Unfortunately, we use zeros to hold place value. So from the way this measurement resulted, we don't know if they were able to measure the 1 spot. They may have been able to, or they may not have been. So we don't know about that one. So it may have 2 sig figs. We don't know if they're able to measure the 10 spot or not, or if they were just using it to hold place value. So it may have 3 sig figs. We don't know if they're able to measure the 1 spot or not. So it may have 4 sig figs. So this could have anywhere from 1 to 4 sig figs. In my mind, what they have done is they have encouraged sloppy habits. They would argue that what they're doing is teaching conversational real-world chemistry, and I'm saying they're enabling bad habits, because I would argue they should have put it in scientific notation, right?
Right.
And this ambiguous zero rule only applies when you're just looking at that measurement, right? When you're looking at that measurement, you'd have to say, well, it could have 1 to 4 sig figs. When push comes to shove, and I were to ask you, what the area is there, you're going to treat that as though it had only 1 sig fig. Yeah. See, so even the book admits their own flaw of the flaw in their own logic there. That having been said, we had an adjunct who who worked a long time in industry, and he believed in this ambiguous zero thing because that's the way you communicated with other chemists.
Oh, wow.
Right? If I told you to make up a solution, I would tell you go make me up a 3,000 milliliter solution, and I'm just going to assume that you're going to grab a graduated volumetric flask off the shelf that's calibrated to the ones, right?
Right.
Basically, what they're doing is they're kind of trying to give you the idea that when chemists talk to each other, they kind of know what they're talking about in each other's capabilities, and therefore it's kind of this ambiguous gray area. Whereas I argue they should be teaching you publication etiquette, correct communication etiquette, if that makes sense.
Right.
3,000 is a little bit of an extreme example. You're sorry you asked this question now. Where the situation's a little bit more clear in the case for the ambiguous zero argument is you'll see it in the lab instructions, is when you're looking at like 100 milliliters. If your lab doesn't have the ability to make up a 100 milliliter lab solution that's accurate to at least the ones place, then your lab is a pretty pathetic one indeed, right? And you wouldn't find a chemist in their general conversational writing or giving lab instructions to a grad student who would say, make me a 100.00 milliliter solution, or they wouldn't say, make me a 1 times 10 to the second milliliter solution. They would just say, go to the lab and make me a 100 milliliter solution. And there they would not only assume that it was going to be accurate to the ones, quite frankly. If I requested very nicely of Dariana to make me a 100 milliliter solution, I would just assume that she actually made it to the hundredths place accurately, given the glassware in the lab. But that's where the ambiguity, wow, I sounded like Bullwinkle there, rule for those zeros comes from.
Okay, thank you. I was
analytical chemist went down one of my favorite rabbit holes
there, but they didn't specify the ambiguity, so I didn't know what they were talking about when they put that on there.
Yeah, that was the one I was trying to warn you guys about in lecture in terms of the checking the boxes.
Yes. Yes.